Okay, so in our last class, we were going through some basic examples of ladder diagram programming. Now here, let us start with another example. So this particular example can be called designing a first priority circuit. Okay, so according to the description, that a circuit has to be designed for a quiz game of 3 participants, and if any participant wants to answer a particular question raised by the host, the participant must press the answer button on their table, and who presses the button first, he will get the opportunity to answer the question. And the lamp is supposed to be associated with the respective table of the participant. From the indication from the lamp will assist the host to determine which participant has pressed the button first. Once a participant has pressed his button, the other participant's input should be disabled or made invalid. So that is one of the conditions that has to be satisfied while designing this particular system. And the host will have an overall option to reset the whole system before asking the next question. So according to the description, if we consider the input devices, we can say that 4 push buttons would be necessary. So one of the push buttons should be for the host in order to reset the entire system, and 3 other push buttons for the 3 participants. And as output, that is 3 lamps or LEDs to indicate the participant who has pressed the button first. Now, the relation between the inputs and outputs has to be established in form of the ladder diagram or ladder logic program. The output connection is quite straightforward. I mean, external connection to the board is quite straightforward, using similar pattern that has been discussed in the previous classes as well. Connecting the input push buttons to a specific input ports, 4 different input ports, and connecting the output lamps in the output ports, and along with the necessary DC supply. Now, the ladder logic program to implement the system described in the previous slide. These input devices through their port address should be related to the output devices, relating them to the addresses of the output ports. So, considering the discussions on the previous classes, I think some of you can suggest how we should proceed with this. Let's say this is one vertical rail, this is another vertical rail. So in between the 2 vertical rails, how should we proceed in order to structure the system which was discussed earlier? Anyone? You can think of one participant at a time. So let's say for the first participant, what should you do in order to take input from the first participant? Okay, no response. Now, in order to take input, you have to somehow, let's say this push button 1 is associated with the button for participant 1. So this address has to be related with this address of this output port P40. So in order to take input from the participant 1, should we use a normally open contact at the input side or a normally closed contact?
So normally open.
Okay, yes, normally open should be taken because we want to close this contact once there is some input, otherwise it should remain open. Now along with this, we have to relate this output port, right? So on the output side, we should place a coil like this. The addressing of this particular normally open contact should be P01 in this case, and uh, for this input we want to trigger output connected at P40. So the address of this output coil should be denoted as P40. Now these are push buttons or momentary switches. So once the participant has pressed the button, then released the button, the contact is supposed to be in its initial state again. So in order to provide continuous path for the output, what should we do? Did anyone even follow last class or have gone through it later on?
Yes, sir.
So do you remember that a portion was discussed called latching the output in order to create a bypassing path?
Yes, sir.
So what was done in that case?
So we take the output with latched with the input as parallel, sir. Maybe, sir, I don't actually remember.
So a contact with the address associated with the address of the output port is taken in parallel with the original contact in order to create a latching path or a bypassing path. So whenever this push button is released, button 1 is released, this path is again going to be open, but once the coil is energized for the duration when button on P01 was pressed, this coil was supposed to be energized, and this is supposed to trigger this particular contact. So even if this button on port P01 is released, as this contact is already closed, a bypassing path would be there. Similarly, in order to take input from the other participants, similar configuration can be used. These are only for taking inputs from each individual participant. But there was a condition in the statement that if a participant presses the button first, inputs from other participant should be disabled. Even if the other participant press their button, they should not actuate any output towards their respective output ports. So in order to disable the input from the other users, when one particular user has pressed his button first, what modification can be done? Okay, let's say participant 1 has pressed the button first, then we have to disable the inputs from participant 2 and participant 3. So we have to somehow open this path and this path when participant 1 has pressed his button, so that opening this path will disable the inputs from the other users. In order to do that, normally closed contacts associated with P40 can be placed along these paths. So when participant 1 is giving some input before participant 2 and 3, this coil is going to be energized. When it is energized, it will close this normally open contact and it will cause these normally closed contacts to open up. So if these contacts are getting transition from their initial state, so if initial state is considered to be 1, after transition they are going to be 0, or in this diagram representation they will become open circuit. Even if participant 2 gives some input, due to the open circuit, there is no continuous path up to the output coil. Similarly for participant 3 as well. So for each individual participant, we have to consider this scenario. So for participant 2, we also have to consider the scenario of participant 3. What would happen if participant 3 presses the button first? Then we should place another normally closed contact in series with the other one. Here we should consider the fact of participant 1 and participant 2. So it should be P4 1. And here we should take the consideration of participant 2 and participant 3. If somehow they presses the button first, this respective path should be open so that the connection from the left hand rail and this output coil is not established. Apart from this, there was another thing that the host has the option to reset the entire system. So the reset button that is going to be used by the host is connected with port P00. So how can we take this port into consideration in order to reset the entire system? Now you should at least be able to give some suggestion.
So we can connect P00 on all of the branches, and when it's pressed, the circuit will open. Is it something like that?
Okay, so yes, that could be one possible option. Connecting normally closed contacts in all the 3 different lines. associated with the port address P00, so that when the button on P00 is pressed, these contacts become open and initialize the de-energize all the output coils and uh, take the entire system into its initial state. Now, this option is definitely going to work. Another option could be to place this normally open contact at the very beginning along with the vertical rail, left hand side vertical rail. So that is actually going to do the same task because it is going to disable the entire circuit on the right hand side portion from the left hand side rail, and it would not be necessary to put separate contacts on each of the individual lines. So both of the options will work here. However, the second approach could be better to adopt. Now, once the instructions are given, the set of instructions are given in terms of diagram, then the user should insert an end or return block that may vary depending on the manufacturer. So the user should insert an end block so that the PLC or CPU will start or jump to the first line again and continue the scanning process. So it is a continuous process, like a continuous for loop. It would go on until the user intentionally interrupts the power supply or stops the entire process. Now, this same ladder logic program is shown over here, which is drawn using the software. Now we are discussing about XGB PLC series to get accustomed with the PLC board that we have in our lab. And for this PLC series, the software used to uh, 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 construct this ladder logic diagrams is XG5000, which is compatible with this PLC series. And this particular diagram is drawn in that particular software. So the same diagram has been drawn over here. Now in this case, let's say no button has been pressed yet. No participants has pressed any button, and the host has also not pressed the reset button. So this would be the initial condition of all the contacts and the coils. So all the normally open contacts are open. The normally closed contacts are closed as indicated by the blue dots, and the output coils are also not energized. They are also shown to be open because they are not receiving any complete path because of these normally open contacts. Now when button 1 is pressed, which is connected at port P01, then the contact associated with this particular uh, port should be having a transition. So it was previously normally open, now it should be closed. Or in terms of memory bits, you can say that the bit was initially set to 0, now it is set to 1. So now there is a complete path for this output coil at P40. So it will also have a transition, or we can say that it will get energized. So it will actually get, after getting energized, it will trigger this particular contact, which is associated with the same port address P40. So this contact was also previously normally open. Now it will also become normally closed. Now, even if the participant releases button 1, as these are momentary push buttons, when the participant releases the push button, this contact associated with port P01 would go back to its initial state, because now the port is not receiving any signal. But as a bypass path was already created in terms of the port address of the output port, so following this bypass path, the output port P40 is still going to get continuous signal, and the output device that is externally connected to this port will also have proper power supply. So the lamp connected with that port will be still glowing. At the same time, these contacts were also associated with the same address P40. So whenever this coil got energized, P40, these normally closed contacts become normally open. And this contact was initially normally open, it became normally closed. So as these contacts have become normally open, this path is getting open circuit now, this portion of the line. So even if participant 2 or participant 3 presses their button, there is not going to be any continuous path for these output ports P41 and P42. Like indicated over here, that even if participant 2 presses his button, this port is going to become normally closed. However, as this was already, this contact was already opened, so this will not cause this particular output to get a high signal. So in this way, as the participant 1 pressed the button first, the input from the other participants can be disabled. Now to go back to the initial state again, the host can press the reset button. And when the host presses the reset button, this contact associated with port P00 will have a transition from 1 to 0, or from being normally closed to normally open, and it will disconnect this entire portion on the right hand side from this left hand power rail, and thus all the output coils will get de-energized and the system will be in its initial state again. Any question up to this?
No, sir. Understood.
So in the later part, I am going to discuss about the different types of timers that can be used in this PLC board. Before going to that, I want to discuss something about the memory segmentation, which might give you a basic idea about the addressing that is done for the input output ports and the other segments as well. And this is for the XGB series. Now for different, in XGB series there are different models available. So for different models, the segmentation is almost done in the same way. However, the memory allocated to each segment might be different depending upon the model. So we can have a table over here. So the user RAM is normally divided into several segments, and each segment is annotated with a particular character. Let's say one you can already suggest, that is P, to indicate the physical input output ports. So it is normally for manipulating the data between or the input and output ports or input output devices. To this segment of the memory is used to store input output data and also process the data while executing the program. Then another segment is denoted as M, which are internal memory bits. Now, apart from the physical ports, some internal memory bits might be necessary to while constructing the ladder diagrams. In the previous examples that we have seen, we have directly related the input port with the output port, but it might be necessary that in between the input and output there might be some intermediate stages or some intermediate operations needed to be done. So if that is the case, then the internal memory bits can be used. For the physical segment and the internal memory bit segment, the addressing is done in almost similar way. So the address starts with P, the segment annotation, then some numeric values, and the addressing is normally from P0000 and to 1023F. For internal memory bits as well, similar addressing is used for the rest of the segments as well. Now, what are the other segments? A portion of the segment is defined as uh, denoted as L, which is actually used by the CPU in order to link up or communicate with external devices or the PC or the connection between PC and CPU. So uh, this is for the communication purpose. This portion of the memory is used. Similar addressing is done for this portion of the memory as well. Then K, this area of the memory is used to preserve data in case of any power shutdown. So in order to preserve some data in, uh, to account for power shutdown, the CPU can store some data into this portion of the or this segment of the memory. F is for system flag. The CPU can use this portion of the area to manage different flags necessary for the operation of the PLC. And there are other segments for timers and counters. So in order to initialize the time delay, these portions of the memory can be used. And for setting up a counter, the memory segment designated for the counting operations can be used. Now these three portions are normally used by the CPU. Other segments are normally available to the user. So while constructing a ladder logic diagram, the user can use these portions of the memory. The addressing for the timing segment is normally from 0000 up to T1023. Now the addressing for the timer and counter are done in a little bit different way. As you can see that for the physical ports and the memory bits, internal memory bits, In the addressing, there is an extra digit. However, in case of timer and counter, that extra digit is not present. So normally, the number of addresses may differ from different model to model of different PLCs manufactured by LS brand in their XGB series. But in general, this can be indication of the different memory locations available to the user. Now, while we were looking at the previous examples, maybe we have denoted the address to be P40. So that is a short form to denote the address. However, while we are writing the address to be P40, actually the address should be P0004, then this additional 0, which is representing this extra digit. So that would be the actual address, but as the first 3 digits are 0, that's why in short form the addressing is denoted like this. However, in the software you would see that the full addressing is shown. Now let's say for the physical or the internal memory bits, let us try to see what the addressing indicates. Let's say there are these 4 digits and an extra digit available over here. So this last digit actually indicates the bit position, and this last digit is normally represented using hexadecimal numbers. These 4 digits at the middle, they are representing word number, and these 4 digits can contain the numbers from 0 to 9, or they can contain decimal numbers. However, they're, for most of the PLCs, they are limited from 0000 up to 1023. And this first portion, it actually indicates the memory segment. Now, before indicating, I mean, the I mean, the significance of this, I mean, 4 digits. Let's say you know how many bits are there in a byte, right? There are 8 bits. Now, I think you are familiar with the representation in terms of word, right? So how many bits are in a single word?
16 bit.
16 bit. So these 4 digits, or this number, which is a decimal number, represents the a particular 6-bit word. Okay, each particular number represents a particular word or 16 bits memory location. So that is why these 4 digits are called word number. And among the 16 bits, which bit we want to indicate specifically, that is indicated by this bit position. So it could be from 0 to F. So you know, for hex digits, 0 to F they contain 16 different numbers. So using these hex numbers, among the 16 different bits for a particular word, which bit is being indicated, that is denoted by this last bit. So for example, let's say there are 16 bits available to us. Let us consider the first one. Let's say this is the 0th word. If this is the 0th word, which is containing 16 bit, we have to write like this. And if we want to indicate to a specific bit among these 16 bits, we have to write the corresponding hexadecimal number. So if we want to indicate the first bit, we can place a 0 over here. So that would indicate to this particular memory bit. Then for this 0th word, if we want to indicate, let's say, the 15th bit, then we have to place an E. So that would indicate to this particular memory bit. In this way, there are from 0 up to 1023. So in total, 1024 different words, and each words contain 16 bits of its own, and each bit is represented by the corresponding hexadecimal number in the address. So from 0000 up to, let's say, P1023F, which is this one, let's say. So there are different memory bits. So let's say if I ask you from 0 P00 up to P1F, how many memory bits will be available to you? Anyone?
Can you repeat the question?
From P00 up to P1F, or let me say P00000 up to P0001F, how many bits should be available to the user? First of all, tell me how many words should be there.
So one word 16 bits, sir. So yeah, so there is only 4 available for representation. 4 bits.
Okay, so this is representing one word. Okay, this is
Yes, sir.
representing another word. So how many different words we have? 2 different words, right?
2 different symbols.
If there are 2 different words and each can contain 16 individual bits, so what should be the total available bits?
2 into 16.
It's 32. Okay,
Yes, sir.
just a moment. Okay, now let's say if you have P 00000 to P1023 if this amount of different memory locations, so how many different bits should be available to you? So from 0 to 1023 there are total 1024 different words. Each word contains 16 bit. So 1024 multiplied by 16, which would be 16,000 something. So that amount of bits are available in between these memory locations.
Yes, sir.
So the word number can be considered to be the maybe the number of a road, and the different bits can be considered to be the number of the houses. So let's say this is the zeroth word. So this is the number associated with this particular word, and each of the bit has a unique representation in terms of the hex digit. In this way, for 0001 up to all the way to 1023. Now, if I discuss about the timers, so for the timers, the addressing is done in a different way. So there are 1024 different timers available. However, their addressing only contains the word numbers. Each bit is not represented individually. So in terms of the word number, the addressing of the timers and the counters is done. So from zeros to up to 1023, there are 1024 different timers that can be used in the XGB PLC. Now those timers can be categorized into 3 categories depending on their resolution. Now resolution, or you can say the step size, that in each step how much delay will be generated. So based on that resolution, 3 categories: 100 millisecond, 10 millisecond, and 1 millisecond. 3 different category of timers can be there, and the respective addresses of each type of timer is given over here. So the timers that have 100 millisecond resolution, their address is from T000 up to T499. So 500 timers are available with 100 millisecond resolution. For 10 millisecond resolution, there are another 500 timers from the address T500 to T999, and the rest of the 24 timers from T1000 to T1023, they are having a resolution of 1 millisecond. Now in order to generate a specific amount of time delay, this relationship can be used, which is quite straightforward. Now here y represents the expected time, or the amount of time delay to be generated. R is the resolution, and T is the time constant. For example, using a 100 millisecond timer, you want to generate a delay of 5 seconds. So your y is equals to 5, R is equals to 100 millisecond, and T, the time constant, you have to set accordingly in order to obtain this 5-second delay. So while drawing the ladder logic instruction, you have to mention the time constant, which would be in this case 50, in order to generate the 5-second delay using a timer having a resolution of 100 millisecond. Similarly, you can do the calculation for 10 millisecond, 1 millisecond as well. So for 10 millisecond timer, in order to generate a 5-second delay, the time constant t should be 500, and accordingly for 1 millisecond timer you can also calculate it very easily what should be the time constant. Now that was classification of the timers in terms of the resolution or step size. Now in terms of the application or function of each timer, they can be divided into 5 categories for doing ladder programs for XGP series. Now they are on delay timer, off delay timer, integration or momentary delay timer, monostable timer, and re-trigger timer. And their notation that has to be used while constructing the ladder diagram, those notations are specified inside the parentheses. Now if we discuss about the on delay timer, let me first discuss a little bit about the instruction or the symbol, how it looks like in the ladder diagram. So this is normally the representation in the XG5000 software, where 3 different information has to be inserted by the user. The first of all, the first information designates the type of timer. So if someone wants to use the on delay operation, then T on has to be written in the timer as the timer type. Then the second block, this capital T actually indicates the address of the timer. So starting from T000 up to T1023, any one of the address can be used, but uh, considering the address, the corresponding resolution has to be considered while setting the time constant, which is inserted into the third block or as third information. So this is the time constant. So if someone uses a address of the timer from T000 from to T499, then they have to keep in mind that the resolution of these timers are 100 millisecond, and the time constant has to be set according to this particular resolution. Now the notation for all the different types of timers are same, just in case of this first information, the timer type, that has to be changed in the notation of each different type of timers. These timers are normally connected as an output device in the ladder diagram. So in the ladder diagram, they are supposed to be coupled with some input device through the address associated with a particular input device. Let's say P00, and let's say this is the timer. So they are always connected at the output side. When they receive some input pulse, in terms of this closing or opening of the contacts, the timer starts its operation. For the on delay timer, when there is some input triggering pulse or at the positive edge of the input trigger pulse, let's say the input contact is having a transition from low to high. So at the positive edge, the timer starts its operation, and for on delay timer, the timer starts its count and continues the count up to a period specified by the user. When the counting is finished, the delay count is over. After that duration, the timer output goes to a high state. So this address, let's say if it is T00, it initially remains at logic level 0. Whenever the delay count is over, then the output of the timer has a transition from 0 to 1. Now the timer keeps operating as long as the input pulse is there. So as long as the input pulse will sustain, the timer output will also remain high. And also the delay count will go on if the input supply is uninterrupted. That's why this term over here is mentioned, that without interruption, after the delay period is over, the timer output will go high. For example, this is the delay period up to which the delay has to be generated. Before the delay duration is over, if the input pulse goes to low, let's say at this position, then the timer will stop its operation. The timer output will not go high, and the delay count will also stop. This is characteristics for on delay timers. But if the input pulse sustains for a longer duration, that the delay period can be, or the duration of the delay count is finished, then the timer output goes high as long as the input stays high. The second type of timer, the off delay timer. In this type of timers, whenever the input pulse goes high, the timer output at the same time goes to high state as well. It continues to remain at high state, and when the input pulse has a transition from high to low, the timer delay count starts. So the count delay will be counted, for the duration set by the user, and for this period of time the timer output will also remain high. Whenever the delay count is over, the timer output will go to low again. So this is how off delay timers operate. The third type of timer is integration or momentary delay timer. For this case, the operation is a little bit different from the on delay timers. Now, for this type of timers, the timer output normally remains initially at low state, as indicated over here. Now, the timing delays are counted separately as the input at different input pulses are fed towards the timer. Let's say one input pulse has a duration of t1, another input pulse has a duration of t2, and there is a third pulse that has a duration of t3. Now user has set an overall delay that is equal to y, and let's say t1 is less than y. t1 plus t2 is also less than y. When there is this third pulse with t3 duration, let's say t1 plus t2 plus t3 equals to the time delay set by the user. So at that time the timer output will go high. So the duration of the individual pulses will be integrated, or they will be accumulated together, and when their individual durations, sum of their individual durations is equal to the delay set by the user, then the timer output will go high. But in case of on delay timers, it can operate depending upon only one pulse, and if that pulse is taken off somehow when before the delay count is over, the timer will stop operating. But in this case, delays of or duration of each input pulse is summed up together or integrated together, and when the duration is equal to the duration set by the user, the timer output goes high. And the notation for the momentary delay timer is TMR. So in the instruction, the user has to denote this type of timer by the same notation. The other type of timer is monostable timer. So how this sort of timer operates? So upon receiving an input pulse, at the positive edge of the input pulse, the timer output will go high. At the same time, the delay count will start, and the delay count will go on for the time period set by the user. In between this counting process of delay, if the input pulse goes low, the delay count will still continue, and within this duration, if there is another input pulse, now this sort of timer will not have any effect of any intermediate pulses between the period when the delay count is going on. And as long as the delay count is going on, the timer output will also remain high. And when this delay count is over, the timer output will go from high to low. So the characteristics of this sort of timer is that once it is triggered to start the delay count, it completes the delay count irrespective of the status of the input. And once the delay count is over, the timer output also has a transition from high to low. Now the last type of timer is retriggering timer, and its operation is slightly different from the monostable timer. Now initial step is similar to uh, the operation of monostable timer, that upon receiving an input pulse at the positive edge, the timer output goes high, and also the delay count is initiated. Before the delay count is over, if there is another pulse, uh, the timer will actually restart the delay count. In that case, let's say that the user has set a time duration of the delay of this length, as I indicated through the red line over here. Before this duration, if there is another pulse at this point, which is denoted over here as T2, the timer will start its delay count from the beginning again. So from here, it has restarted the delay count, and it will go on as long as the uh, uh, I mean the time duration set by the user is not over. So through this entire process, the timer output will remain high. And let's say if there was another input pulse over here, T3, at this point, before the delay count is finished, then from this point onwards, the timer would have restarted the count up to the duration set by the user. So what is the difference between the monostable timer and the retriggering timer? ID 09. ID 09 seems to be connected in the meeting. Okay, if no response that I can consider ID 09 to be absent. Let's see. ID 33 also absent. Or 33 is here.
Yes, sir, I'm here.
Okay, so can you state the difference between the monostable timer and the retriggered timer?
Sir, can you repeat the question?
In the previous slide, I discussed about the operation of monostable timer, and in this slide, I discussed about the operation of retriggering timer. I asked you what is the difference between the two timers operation or their operating principle.
Mm.
Is there anyone who can suggest?
So on retrigger timer, the output will remain high after getting the impulse pulse. But in case of monostable timer, the period will start counting from the beginning.
Well, upon receiving the pulse, the output goes high for both the monostable timer and the retriggering timer. So in this point, there is no difference, but what is the difference, or in which consideration you can say that there is a difference?
So in monostable, there is no interruption signal.
Okay, according to this diagram, the delay count has been initiated. What will be the effect of this other input pulse? Will there be any effect, or
No,
the
sir.
timer will continue its count?
It will continue.
And in case of retriggering timer, what will happen?
So it will it will
Also, you can
so it will
say it
it will
from its
it will
name.
count.
What
So
is the
it will
name?
count, but it will retriggering.
It will retrigger the counting process again, right?
Yes,
Or
sir. Initiation.
restart the counting process from the beginning again, as it wasn't
Yes.
finished before receiving this second pulse. So if the delay count is not over within that period of time, if there is a second pulse, then the counter will start counting from the beginning again, or it will get re-triggered. But in case of monostable, it has a single stable state. Once it is initialized, the counting is initialized, irrespective of the changes in the input device, The timer will finish the count, then look for or scan for the status of the input bits.
Yes, sir.
Okay, so let me keep the discussion up to this for today. But if you are not understanding during the class, you can raise a question. I can try from my side to clarify. But not getting response when I am asking you some question means that you are just connected in the meeting doing nothing. So that is almost equivalent to being absent in the class. So even if you are not asking any question, try to follow what is being discussed in the class so that when I ask you something, at least you can answer something